Today, in section 7.3, we will be talking about multivariable functions. Multivariable functions are just like functions that we've been dealing with for this entire semester, except they take in two inputs and produce one output. So instead of just f of x equals y, what we have is f of xy equals z. Now, this may sound really complicated, but it's just the same thing that we've been doing. You've been doing it your whole life. You just haven't been calling it a multivariable function. So one example, I think the easiest example of a multivariable function is the area of a rectangle. So here I've drawn a rectangle with height x and width y, and if we want to calculate the area, we take in x and y as an input, and we multiply them together. So the area of a rectangle, given length x and width y, is just x times y. So if I tell you x equals 5 and y equals 2, then the area of 5, 2 is just 5 times 2, which is 10. Okay, with that in mind, let's take a look at some more complicated examples. Given f of x comma y equals 2x squared minus y squared, find f of 2, 3. So here our x equals 2 and y equals 3. 2 is the first input, 3 is the second input. 2 corresponds to the first input being x here, and the second input 3 corresponds to the second input y. So now that we know that x equals 2 and y equals 3, we just plug in 2 whenever we see x and 3 whenever we see y. So f of 2, 3 equals 2 times 2 squared minus 3 squared, which is 2 times 4 minus 9, which is 8 minus 9, which is negative 1. All right, now for a function with three variables. Given f of x, y, z equals e to the x times y plus z, find f of 0, minus 1, 4. 0 being our first input means that x equals 0. Minus 1 being our second input means that y equals minus 1, and 4 being our third input means that z equals 4. Okay, and so with that in mind, we can just plug those numbers in. So we get e to the 0 times minus 1 plus 4, and that works out to be, well, e to the 0 is just 1, because anything to the 0 power is just 1. Minus 1 plus 4 is equivalent to 3, and so 1 times 3 is 3. And that's your final answer there. All right. Let's talk about domain and range of multivariable functions. So the domain of f, if f is a multivariable function, is the set of all ordered pairs for which f of x, y is defined. The range of f is the set of all possible outputs of f. For functions of 3, 4, or more variables, domain and range are defined similarly. Basically, it's the exact same thing that it was for one variable, but instead now there's multiple inputs. So let's take a look at this in practice. We want to find the domain and range of f of xy equals the square root of 64 minus x squared minus y squared. Remember, domain is the set of all allowable inputs, so I like to think about what is the set of not allowable inputs. What inputs break the function? Because we're dealing with a square root, we cannot have 64 minus x squared minus y squared be negative. Because if 64 minus x squared minus y squared is less than 0, then the square root isn't defined. So what we know is that 64 minus x squared minus y squared is definitely greater than or equal to 0. We can add an x squared and a y squared to both sides. So that gets us 64 is greater than or equal to x squared plus y squared. What we get is x squared plus y squared is less than or equal to 8 squared. Okay? Now, if we think back all the way to day 1 or 2 of the semester, remember that the function x squared plus y squared equals 8 squared defines a circle of diameter 8. So if I draw a quick little xy axis here, this x squared plus y squared equals 8 squared is this circle here, assuming the circle has diameter 8. So the set x squared plus y squared is less than or equal to 8 squared is not just the circle, it's also all the points inside here. Okay, so this is our domain, and graphically it looks like this. But now that we know our domain, how do we calculate the range? So remember, the range is the set of all allowable outputs. So if we put something in from our domain here, what are the possible outputs we can get? So let's think about it like this. Let's think about what's the smallest value for an output we can get and what's the biggest value. Well, what's the smallest input we can have? The smallest input is if x and y are both 0. So if x and y are both 0, then f of x comma y is f of 0, 0 equals just the square root of 64, which is 8. Okay? So we know that our output values, and we'll call those z, have to be less than or equal to 8. They can't be bigger than 8. And if we plug in bigger values for x and y, well, the biggest values for x and y that we can get are ones that actually equal 8 squared, right? Because we can't have them be bigger than 8 squared, but we can have them go up to 8 squared. So something that works is x equals 8 and y equals 0. So if we plug in f of 8, 0, what we end up with is the square root of 64 minus 8 squared minus 0 squared. But 8 squared is just 64, so this ends up being the square root of 0, which is 0. So that tells us that our outputs have to be bigger than or equal to 0, and so that tells us our range is between 0 and 8. All right, just one more section in this video, and that section is the Cobb Douglas production function. It's as exciting as it sounds. The Cobb Douglas function is used to calculate the number of units produced by varying amounts of capital and labor. If x is the number of units of labor and y is the number of units of capital, then the number of units produced is modeled by f of xy equals c times x to the a times y to the 1 minus a, where c and a are constants with 0 less than a less than 1. So we usually don't have to calculate c or a. Those will be given to you. What we need to do is, given an x and y, calculate the output. A manufacturer estimates that its production, measured in units of product, can be modeled by f of xy equals 100 times x to the 0.6 times y to the 0.4, where x is measured in person hours and y is measured in thousands of dollars. So thousands of dollars we're all used to. Let's talk about person hours. So a person hour is units of labor. If I have one employee that works 10 hours, that's 10 person hours. Or if I have 10 employees that each work 1 hour, that is still 10 person hours. So that's what person hour means, is it's hours of labor put in. We want to find A, what is the production level when x equals 1,000 and y equals 500? And B, what is the production level when x equals 2,000 and y equals 1,000? Well, this is just evaluating the function like we did earlier. We just plug in our numbers. So f of 1,000, 500 is just 100 times 1,000 to the 0.6 times 500 to the 0.4. And recall here that I'm plugging in 500 for y because 500 is our second input, and 1,000 for x because 1,000 is our first input. And if you plug this into a calculator, what you'll get is 75,286. Okay, so let's turn our attention to B. We want to find f of 2,000, 1,000. And so that will be 100 times 2,000 to the 0.6 times 1,000 to the 0.4. And now if you plug that into a calculator, what you'll get is 151,572. Now what's interesting about this is that 151,572 is 75,286 times 2. It's twice the first amount of A, or it's twice the amount we found in A. So what this tells us is if we double the amount of person hours and the amount of capital we put in, we will double the production. Which makes sense. If I double the amount of employees and I sink even more investment into a company, then the output, the number of production, the amount of production will increase proportionally.